Hello, discrete math fans. So we've been talking a lot about relations that are reflexive, symmetric, and transitive. And a relation that satisfies those three properties has a name. It's called an equivalence relation. So anytime you have a relation that's reflexive, symmetric, and transitive, it's called an equivalence relation. Let's look at a few examples. Now I think you should take the time to write a proof for each one, proving that it is an equivalence relation. That is, you have three things to prove: that it's reflexive, symmetric, and transitive. Now don't skip over this. You should pause the video after each one and write out a proof that each one is reflexive, symmetric, and transitive. Don't skip over this. You really need this kind of practice. All right, here's an example. Let X be any finite set, and we'll define a relation R on the power set of X by saying that if A and B are in the power set of X, then A is related to B if and only if A and B have the same number of elements. Here's another one. Let's let L be the set of strings of length 5 over the alphabet AB. And we'll define a relation on L by saying that for any S and T in L, so S and T are strings of length 5, S is related to T if and only if S and T start with the same two characters. Here's another one. Define a relation R on the integers by saying that for M and N that are integers, M is related to N if and only if 7 divides M minus N. So all three of these are examples of equivalence relations. You should prove that each one of these is an equivalence relation by proving that they're all reflexive, symmetric, and transitive. Now you should note that in the last equivalence relation, there's really nothing special about 7. We could replace that with any non-zero integer and it still works. You'll have a different relation, but it'll still be an equivalence relation. Well, now let's go ahead and run through the proof that this last relation is, in fact, an equivalence relation. So there are three things that we have to prove. We have to prove that it's reflexive, symmetric, and transitive. All right, so for reflexive, let's let M be an integer. And we note that M minus M is equal to 0, and that's divisible by 7. So that tells us that M is related to M. And that's what we need in order for the relation to be reflexive. All right, let's prove that it's symmetric. Let's let M and N be integers, and we'll assume that M is related to N. What does that mean? That means that 7 divides M minus N, so we can write M minus N as 7k for some integer k. All right, then if we flip it around, we take N minus M, we'll factor out the negative sign, and now this M minus N can be replaced with k. And if we put the minus sign on the inside, we know that minus k is still an integer, and so that tells us that 7 divides N minus M, and thus N is related to M. That means we can conclude that R is symmetric. Last one, transitive. Let's let M, N, and P be integers, and we'll assume M is related to N and N is related to P. That means that 7 divides M minus N and 7 divides N minus P. And that means we can say that there exist integers j and k such that M minus N is equal to 7j and N minus P is equal to 7k. All right, so if we work with M minus P, we can write that as M minus N plus N minus P. Of course, we can write that as 7 times j plus 7 times k. And we factor out the 7. And then that tells us that 7 divides M minus P. And so that tells us that M is related to P, and that means that R is transitive. So we've proven it now, that this relation is reflexive, symmetric, and transitive, and that makes it an equivalence relation. Okay, that's all for now.